In this session, we will discuss the average orders of basic arithmetical functions. Last time, we had proved some results which will be helpful in this session. Okay, so first let us define what is the average of an arithmetical function. So the average of an arithmetical function f, small f, is capital F from r plus to r, where f of x is 1 by x times the summation of all n less than or equal to x, f of n. Here this n is going to take only natural numbers less than x. So this is the average of an arithmetical function. You can notice here that when x is a natural number, say capital N, then what this gives you is 1 by capital N times summation small n going from 1 to capital N f of n, which is exactly the average of f from 1 to n. Okay, so before we proceed, let us prove a basic result, that is the number of multiples of t less than x is the greatest integer of x by d. So let us prove this. It is quite an obvious result, but I would like to prove it just for the completeness of the course. Okay, so what are the multiples of d? The multiples of t are going to be 1 times d, 2 times d, 3 times d, and so on, right? And you want the multiples less than d, so you're looking at 1 times d, 2 times d, 3 times d, up to m times d, where m times d is less than or equal to x, and m plus 1 times d is greater than x. This is what you're looking for. Therefore, what are you looking for? Therefore, what are we looking for is m such that m times d is less than or equal to x and strictly less than m plus 1 times d. Now we can divide throughout by d, and we notice that m is less than or equal to x by d strictly less than m plus 1. And what does this tell me? So you can see x by d lies in the interval m, m plus 1, which means that the greatest integer of x by d is m. And we know that m is the number of multiples of t less than x. Okay, these are all the multiples of d less than x is 1d, 2d, 3d up to md. Therefore, there are m of them. Therefore, this becomes exactly the greatest integer x by d. So we will require this result in a proof later. So keep a note of it. Okay, one very interesting result is the Dirichlet's asymptotic formula. Okay, so let's see what this states. So Dirichlet's asymptotic formula tells us that summation n less than or equal to x. Again, let me remind you here that n takes only natural numbers less than x. Okay, so n less than or equal to x, d of n, that is the divisors of n, number of divisors of n, will be equal to x log x plus 2 times c minus 1 times x plus big O of the square root of x. Let's see how to prove this. First, you notice here that summation n less than or equal to x d of n, okay, this will be equal to summation n less than or equal to x summation. We know that d of n is, look at all the divisors of n and count them once. Okay, now we can write this in another form. Okay, this is a set of all. Here you can see we are varying n over all natural numbers less than x, and then we are looking at each divisor of n. So we can write this in this form, that is summation k comma d in n2, where kd is less than or equal to x1. Okay, so this is exactly what this works out to be. You can see here what basically it looks like is you're taking n to be kd, or in other words, you're taking k to be n by d. Okay, so this is what you get. Okay, so try to convince yourself that this equality is true, and then proceed to the next part of the theorem. Okay, so you can see here that this counts some lattice points in n2. Okay, this here will count some lattice points in n2. So let us look exactly at what is happening. So let us draw the n2 plane. Okay, so this is your n2 plane. So this is 1, 2, 3, 4. Here also you have 1, 2, 3, 4, and so on. Okay, let us call this as the k-axis, and let us call this as the d-axis. Now we are looking for all those lattice points such that kd is less than x. X here, as you see, is a constant. Okay, so x is a constant. We are looking for all those points such that kd is less than x. Okay, now what does the graph of, say, kd equals x look like? Okay, so you can see here kd equals x is going to be a graph of this form. This is going to be your kd equals x. It's going to be something like this. It is going to look something like y equals 1 by t in the t across y plane. Okay, so this is going to look like this, because so this is, you can think of this as d equals y upon k. Now the less than or equal to section is going to be below this. So you are counting all lattice points that lie in this region, the region below the graph. This is what you're counting. Okay, now a nice observation that you can make is that this graph is going to be symmetric around the line k equals d. Okay, this is going to be symmetric around the line k equals d. So the total number of lattice points under this graph will be the lattice points on this line k equals d plus twice the number of lattice points that are in this region here. Okay, so you have the lattice points in this plus twice the number of lattice points that lie in this region. The lattice points, twice the number of lattice points will take care of this section, will take care of this section, and it will take care of the other section, that is this section. So the number of lattice points here is equal to the number of lattice points here. So therefore we just count the number of lattice points here and the number of lattice points here. The total number of lattice points under this will be the number of lattice points here plus twice the number of lattice points here. So let us see how I'm going to make this count. It's not a very difficult argument. Let us first see how many lattice points are here. Okay, so how many lattice points are here? So the lattice points here, so they should satisfy the lattice points here, sorry. Okay. So the lattice points here should satisfy the equation k equals d. Okay, so they should satisfy the equation k equals d. So the lattice points such that if they have to lie on this line, they should satisfy k equals d, and it should satisfy the inequality kd less than or equal to x. Okay, so two equations should satisfy, which would mean that here substituting k equals d, you will get d square should be less than or equal to x. Or in other words, this means that d should be less than or equal to square root of x. Now here d are only natural number values, which means that d should be less than or equal to the greatest integer of the square root of x. Okay, so d should be less than or equal to the greatest integer of square root of x, and so therefore what you will see here, the number of points that are here will be the greatest integer square root of x. Okay, so now let us count the number of points, the number of lattice points that are in this region. Okay, so let's look at a line, say at some height d. Okay, so let's look at some line at some height d and see how many of the lattice points lie on this line, okay, that are less than that satisfy the fact that kd is less than x. So we know here that this position here is the greatest integer of square root of x. So we can vary d between 1 to the greatest integer of square root of x, and for each of them we will count the number of lattice points that lie in this section. Okay, so you can see just 2, but you might have more if you are lower. So it depends on your x value. Okay, so let's count the number of points that lie on each of these. So how many lattice points lie on this that are less than, that satisfy the equation? So what are the lattice points that lie here first? So the lattice point that lie here will be, you can see that they will be d, will be 1 comma d, the lattice points at height d such that kd is less than or equal to x. This is what we are looking for. So what will they be? So they will be 1 comma d, 2 comma d, up to what? The last point here will be m comma d, where you want md, this is my, so m comma d will be the last sum, you're going to have some m comma d, okay, but now you want this to satisfy the fact that md is less than or equal to x, and you want the m plus 1 times d to be greater, that is m plus 1 should fall on that side. Okay, that's the m which you are looking for. So where m comma d is less than or equal to x, strictly less than m plus 1 times d. Okay, now dividing by d, you again see that x by d will lie in the interval m comma m plus 1. Okay, which means that m should be the greatest integer of x by d. So here you can see that the number of lattice points on this line, okay, on this line, such that that are below the curve kd equals x will be greatest integer x by d. This is what you can see. But now we don't want to count the lattice points that are on this part. This section we don't want to count. So how do I know which are those? This is very easy. So the ones which are on this section will be, okay, so the lattice points if we don't want to count, we do not count the lattice points which are the ones which we don't want to count. 1 comma d, 2 comma d, up to the one that is on the line, that is d comma d. We don't want to count these up to d comma d. And therefore, okay, the required number of lattice points at the height d, okay, so at the height d will be equal to, here you can see there are d, so you can see that in this section here there are d, and in the entire section there are greatest integer of x by d. So the required number will be the greatest integer of x by d minus d, because we don't want to count those extra d. So this will be the greatest integer of x by d minus d. And therefore, you can see the total number of lattice points in the region will be equal to, you will see, that is the greatest integer of x plus twice the number of lattice points that are in this region, that is only in this particular region. Okay, it will be number of lattice points here, which is greatest integer of x, plus twice the number that are here. Now we know, given any d, we know what is the number of lattice points in this section, that is the greatest integer of x by d minus d. So the total number will be, now you vary your d from 1 to the greatest integer of x by d, and you take the sum. So that's what it will be, right? So that will be twice summation d less than or equal to square root of x, or greatest integer of square root of x, that's the same. Here n is varying only over the natural number, so it does not make a difference. X by d minus d. This is what we get. Okay. So therefore what you see here is summation n less than or equal to x, greatest integer of dn would be equal to, by this here you can see that summation n less than or equal to x dn will be equal to twice summation d less than or equal to square root of x, greatest integer of x by d, minus t plus the greatest integer square root of x. Okay, so this is what you see. Let's now try to see what we get from here. So therefore, the greatest integer, the summation n less than or equal to x, d of n would be equal to twice summation d less than or equal to square root of x, greatest integer of x by d, minus twice summation d less than or equal to square root of x, d plus the greatest integer square root of x. Okay, let's see what we have here. So this we will leave the way it is. This will give us twice summation d less than or equal to square root of x, greatest integer x by d. Let us see what this is counting. This counts 1, this sum here. Okay, so this will be 1 plus 2 plus up to, it's going to vary up to the greatest integer square root of x. And we know what this is. This is an arithmetic progression. Okay, actually this is, so this will be minus 2 times square root of x times 1 plus the square root of x, greatest integer square root of x in fact, divided by 2. We can cancel this 2, and we have plus the greatest integer square root of x. This also will cancel, that is greatest integer of x and the greatest integer of x, square root of x, sorry. So this will be twice summation d less than or equal to square root of x, greatest integer x by d, plus, so minus what is left out here is just this into this, that is the greatest integer square root of x, the whole square. Okay, now let me call this as capital 1, because this is important for us, and let us try to estimate this part. Okay, so let's look at the next page. So let us notice this here. If you look at the modulus of d less than or equal to square root of x, greatest integer of x by d, minus x by d. Okay, so this will be less than or equal to summation, because each of these terms is going to be less than 1. So this is d less than or equal to square root of x, 1, and we know what this is. This will be exactly the greatest integer square root of x. This is just going to be the number of integers less than square root of x, number of positive integers less than square root of x, which is the greatest integer of square root of x. And we know that the greatest integer of the square root of x is less than or equal to the square root of x. Okay, so this is one observation which you should make. And what does this tell me? This tells me that you can see here, this happens for every x greater than or equal to 1. Okay, this argument will hold for any x greater than, in fact for any positive x also. So therefore what does it tell me? It tells me that summation d less than or equal to square root of x, greatest integer of x by d, will be summation d less than or equal to square root of x, x by d plus big O of square root of x. This is what we have. Okay, let's pull this x outside the sum. Since it's a constant, we have x times summation d less than or equal to square root of x 1 by d plus big O of square root of x. Now let us use a result which we had proved in the last session. That was, we had shown that summation n less than or equal to x 1 by n. We proved that this was equal to log of x plus c plus big O of 1 by x. This is what we proved. Okay, now instead of x we have square root of x, so this will become x times log of square root of x plus c plus big O of 1 by square root of x plus big O of square root of x. Okay, now what happens when we multiply x inside? If we multiply x inside, we will get x times log of square root of x plus cx plus, now here you can see this function is big O of 1 by square root of x. Notice here that if f of x is big O of square root of x, that means that mod of f of x is less than or equal to some m times 1 by square root of x for every x greater than or equal to some a. This will mean that if I multiply now throughout by x, what do I get is, notice here that x's are all positive, so x times f of x will be less than or equal to m times square root of x. So what does this tell me? It tells me that x times f of x will be big O of square root of x. So if I multiply x to big O of 1 by square root of x, what I get is big O of square root of x plus big O of square root of x. And big O of square root of x and big O of square root of x will give us big O of square root of x, that is x times log of plus. Okay, notice here that I am taking a few shortcuts. If you are not convinced, take the things to the left and prove it on your own. Okay, you need to do the work on your own if you want to really understand. Yes, so we have got some estimate for this section here. Okay, we've got an estimate for this portion. This portion here is quite easy to estimate. Let us look at that. So notice here that, let me label this first as 2. Okay, so you can also notice here that mod of greatest integer of x the whole square minus x, okay, this will be mod of greatest integer of square root of x minus square root of x into greatest integer of square root of x minus plus square root of x. Okay, and this will be less than or equal to, here you can see this term here will be less than 1. So this will be less than or equal to 1 plus twice square root of x, because each of these terms are less than square root of x. Okay, so this will be 1 plus 1 times, this is not plus, 1 times 2 times square root of x, which is, in fact, this tells us that
greatest integer of square root of x, the whole square, will be x plus big O of square root of x. Okay, so we have this, let us call this as 3. Now you put 2 and 3, substitute 2 and 3 in 1. What do you get? We get summation n less than or equal to x d of n would be equal to x log x plus, let us see what is 1. This is 1 here. Now we substitute in this position. What you will have is twice so you have 2 times what you have here is x log root x plus cx plus big O of square root of x. So it is x log root x plus c of x cx plus big O of square root of x. This is what you have. Okay, close the bracket, plus what else do we have is the last term here, which is minus square root of x the whole square, greatest integer of square root of x. But this is x plus big O of square root of x. So this will be, again be, this will be minus x times big O of plus minus big O of square root of x plus big O of square root of x, the same thing. Okay, so now you have twice big O of square root of x plus big O of square root of x. Okay, that's going to be big O of square root of x. By the way, you're not cancelling here. There is no sense of cancelling in this case. Even if it was big O of square root of x minus big O of square root of x, what you would get is big O of square root of x. Okay, 2 times big O of square root of x is the same as big O of square. You have to be a little careful with big O. It is not, remember here that this is not an equality exactly the way you know it. So you have to be a little careful. Okay, now what you get here is twice x times log of square root of x. That will be log of, so x times log of square root of x the whole square, which is x. So what you will get here is these 2 terms are the same. So that will give us I think I have written twice. So here I have made a mistake. This term does not appear. Okay, this term is not going to appear here. This is fine. Okay, so we'll take this out. Okay, so what you get here is x log x, which is x log of x plus 2c x 2cx, and here you have minus 1, so we can have 2 times c minus 1 x plus big O of square root of x, and this is what our result asks us to prove. Okay, so this is what is the Dirichlet's asymptotic formula. Okay, so go through the idea properly. The idea is the most critical. The idea is we are converting this, we are counting something else at the end. Okay, we are counting the lattice points below the curve xkd equals x. That is what we are doing. Use the counting technique and try to do things on your own. So that's the way you would get this. Okay, now let us prove the first corollary, or the only corollary to this, that is the average of dn is of order log n. Let me first tell you what is the meaning of is of order log n. So I will say that the arithmetical function fn and gn are of the same order if they are asymptotic, are of the same order, okay, if the limit as n tends to infinity, f of n upon g of n is infinity. Here, is 1. Okay, so if they are asymptotic, I am only considering n in this case. So let's look at what is the average of dn. So the average of dn we will call as capital D. So let d of x equals limit as, so not limit, what is this function defined as? It is 1 by x times summation n less than or equal to x dn. Okay, I want to say that this has the same order as log n. So what I want to prove is, I want to prove that limit as n tends to infinity, capital D of n upon log of n is 1. Okay, now I know that it is easier for me to work with the x variable, and if I prove that limit as x tends to infinity, d of x upon log of x is 1. Okay, I have given you all to show this as a exercise, then this will hold. So this is what I will be proving. I will be proving this. So this is here. So this we know. Okay, so this is fine. Now therefore you look at what is d of x upon log of x. So what will this be? We know that d of x, that is not in fact d of x, we know that this sum here, what is this? This will be 1 by x times, by the previous exercise, this is x log x plus 2c minus 1 x plus big O of square root of x. So that will be, we remove this, it will be log of x plus 2c minus 1 plus, so this will be big O of square root of x divided by x, which will be big O of 1 by square root of x, just like the previous argument. So this will be big O of 1 by square root of x. Okay, so this is what you have. So d of x upon log x will be 1 plus 2c minus 1 upon log of x plus 1 by log of x big O of 1 by square root of x. What does this actually mean? Okay, so this means that d of x upon log x will be this function plus this function plus 1 by log of x some function which is big O of 1 by square root of x. Okay, that's what it means. Now what happens when x tends to infinity? So limit as x tends to infinity, d of x upon log of x. What will happen here? This will remain as 1. As x tends to infinity, what happens to log of x? Log of x goes to infinity. Therefore 1 by log of x will go to 0. So you'll get 1 plus 0 plus, what happens here? Again you're going to have the same thing. Okay, so as x tends to infinity, 1 by square root of x will go to 0, and therefore any function which is big O of square root of x. What is the meaning of its big O of square root of x? That is f of x is big O of square root of x if after some stage mod of f of x is less than m times 1 by square root of x. So if this goes to 0 as x tends to infinity, this will also go to 0. Okay, so this will also be 0, and we know, so this is function that we know that limit as x tends to infinity of 1 by log x is 0. Also, if this function is 0, so this will be 0, which is 1. Exactly what we wanted to prove. Okay, that the average here, your dx is the average of dn. Okay, so this will be 1, and therefore limit as n tends to infinity, I'm using this fact here. Okay, n tends to infinity, d of n upon log of n will be 1. Okay, exactly what we wanted to prove. So this tells us something very interesting. I will show you all the diagrams here in some later stage, but keep these things in mind. Okay, so this says that if I plot out this dn's, if I plot out the average of dn's, so let me just tell you what this graph is going to look like. Okay, so you can see that, in fact I should have done it for any arithmetical function. So if you have an arithmetical function, let me go back to the definition to make this point a little more clear. So what is this average which you see here? Let's look at this sum just to see what is the sense of this sum. Okay, so this is, so you can see here that if you give me any k and k plus 1 and an x lies here, you can see that the value of this sum throughout this interval k comma k plus 1 is going to be exactly the same. Okay, so here you can see that this sum is going to be constant. Now if you multiply 1 by x to it, it is going to gain this kind of a shape. Okay, it will be something like this, because you're multiplying 1 by x to it. So it's going to be something like this. So this function is going to take the shape something like this. So you can see that it could also drop depending on the function, but it's going to be something like this. So what you can see here, something very interesting, is that the average of an arithmetical function, or not even the average, even the sum which you have here, it is not necessarily continuous, but it is piecewise continuous. Okay, it is not necessarily differentiable, but it is definitely piecewise differentiable. So good functions, piecewise differentiable functions, we know are integrable. So there's a lot of calculus which we can do with it. Okay, this is the reason why we go with, this is one of the reasons why we go with the average of arithmetical functions. Okay, so the behavior of this, the graph of this is what our corollary tells us. It tells us that the graph, this dx, if you graph out your dx, the behavior of the graph of dx will be the same as log x. We know what is the diagram of log x. It is something like this. So it says that after some stage, the behavior of dx is going to be similar to log x. So it will be something of this form. It's going to take the shape of log x as it climbs. Okay, so that's basically what you see. It's still going to be piecewise continuous and not continuous, but it will go up in the speed of log x. That's essentially what it says. Okay. Now one small exercise. This will be useful in the next few results. In fact, in the next result itself. So let us see this. Suppose f of x and g of x are real valued functions, so that f of x is big O of g of x. Then look at this particular function, say capital F. Okay, this will be big O of capital G, if that is the same. So if capital G is this sum, so I'll say let capital F of x be the function summation n less than or equal to x f of n, and I'll take capital G of x to be the function n less than or equal to x g of n. Okay, so this is what I take it to be. Now I know that f of x is big O of g of x. So what does this mean? So f of x is big O of g of x means that there exists some m positive and some a in R such that for every x greater than or equal to a, mod of f of x is less than or equal to m times g of x. This is what it means. Let us take this as m prime. Okay, so we'll call this as m prime. Now we know that these functions here, these two functions, are constant on intervals. Okay, we know that these functions here are constant on intervals. On these intervals they are constant because I am only basically looking at the fn's and gn's, so essentially the respective arithmetical functions by restricting it to n. This is what essentially what I'm looking at. So they are going to be constant here. So let's take m1. Okay, we will take m1. So we'll take m1 to be the number mod of f of 1 upon g of 1. Okay, you'll see why. Okay, if g of 1 is 0, or in fact, yeah, g of 1 cannot be 0 unless f of 1 is 0, because this is greater than this. So g of 1 cannot be 0 unless f of 1 is 0. But in case f of 1 is 0, okay, so you could do this also. If f of 1 is non-zero, and if f of 1 is 0, you take it to be 1. It doesn't really matter. So you take it to be 1 in case f of 1 is 0. And so I'm going to do this. So let me just change this. So I'll take mi to be f of I upon g of I when f of I is non-zero and f of I is 0. This is what I'll take, where I takes all the values from 1 up to the greatest integer of a. See, because I need to somehow take care of the previous few terms. Okay, so that's the key in the proof. Now let m be, okay, I will tell you what m is here. Let m be the maximum of all these mi's and m prime. So m prime, m1, m2 up to m greatest integer of a. This is what it is. Okay, this is what m is. So let's see what we have. So where is my next page? So let us take x to be greater than or equal to a itself. So this will mean that here you can see mod of, so let us look at, yes, mod of f of x, this will be less than or equal to summation n less than or equal to x mod of f of n Okay, and this here we know is mod of f of 1 plus up to mod of f of greatest integer of a plus mod of f of greatest integer of a plus 1 plus up to mod of f of greatest integer of x. This is exactly what the sum will be. Now you can see in this particular case, by the way in which we have taken these mi's, okay, this will be in fact m1 times g of 1 plus up to m greatest integer of a times g of greatest integer of a, and these, so I'll have to make less than or equal to this here, since this is bigger than a, okay, greatest integer of a plus 1 is bigger than a, so this, using this fact here, this will be less than or equal to m prime times g of greatest integer of a plus 1 plus up to m prime times g of greatest integer of x. This is what we have. But all these m's are less than capital M. So this will be less than or equal to m times g of 1 plus g of 2 plus up to g of greatest integer of a. Okay, so you can see here this will be m times capital G of x. So therefore what you see here is f of x is big O of g of x. This proves our result. So what this says is that if f of x is big O of g of x, then summation f of x, summation n less than or equal to x, f of n will be big O of summation n less than or equal to x, g of n. Okay, so another result let's look at, because this is something which we will use often again. Okay, there's a small solution. It's not very difficult to observe this, in fact. So you notice here that the first sum, summation n less than or equal to x, summation d divides n, f of d. This is what we have seen in the previous result, in fact. Okay, this will be equal to summation k comma d in n square kd less than or equal to x f of d. So this will be equal to this, but this sum here, what is this? This will be summation. So a k is going to vary from 1 to the greatest integer of x. So k, if you look at all these lattice points which satisfy this, k will vary from 1 to greatest integer of x, and then d less than or equal to, for each of these k's, the value of d can only vary from 1 to x by k f of d. Okay, so this is something which we will use in the next theorem. Okay, so by the previous result we know that summation n less than or equal to x sigma 1 of n, this will be summation n less than or equal to x summation d divides n d, which will be summation, by using the previous exercise, that is this exercise here, this will be summation k less than or equal to x summation d less than or equal to x by k d. Okay, now we have got one result for this in the previous lecture. So therefore we know that summation d less than or equal to x by k d, we know that this is equal to half of x by k square. Okay, this is what we have proved, plus big O of x by k. Okay, and this will tell us that summation d less than or equal to x by k d minus half of x by k the whole square is big O of x by k. Okay, and hence taking the sum, because this is what we are looking for, we have evaluated this part. So you need to take sum k less than or equal to x on both sides. So what you will get, summation k less than or equal to x summation d less than or equal to x by k d minus summation k less than or equal to x half of x by k the whole square. This would be equal to, here you can see this is big O of x by k, so this will become big O of summation k less than or equal to x by the previous exercises x by k. Which is basically big O of x times summation k less than or equal to x 1 by k. Okay, but we know that, okay, again by results which we have proved in the previous session, we know that summation k less than or equal to x 1 by k, we know that this is log of x plus big O of 1 by x. This is what we know. And this tells us that okay, so it is c plus log of x, okay, c plus log of x plus big O of 1 by x. And this tells us that if I multiply x throughout, I will get x summation k less than or equal to x 1 by k would be cx plus x log x plus big O of 1. Okay, so cx plus x log x plus big O of 1. Now cx, c is a constant, so this is big O of x, and 1 is also big O of x, so this will give us x log x plus big O of x. Okay, we also know that x is big O of log x. Okay, after some stage x will be big O of log x, or big O of x log x, not big O of log x. Log x will be big O of x, but x log x. Okay, so x will be big O of x log x. This is for sure, because x log x will be much faster than x. So this will be big O of x log x. Okay, so what do we have here? So therefore, what we have here is summation n less than or equal to x, sigma 1 of x. Notice here what we have proved. Okay, this is going to be summation k less than or equal to x, summation d less than or equal to x by k d. Okay, now see what we have proved here. We have proved that this minus this is big O of x times summation k less than or equal to x 1 by k, and this here is big O of, because this is big O of x log x, so this will be big O of x log x. So therefore this will be summation k less than or equal to x half of x by k square plus big O of x log x. That is summation k less than or equal to x 1 by 2 times x by k square plus big O of x log x. This would be x square by 2 summation k less than or equal to x 1 by k square plus big O of x log of x, which is x square by 2 times minus 1 by x plus zeta of 2. This is from a result which we have proved in the previous class, plus big O of x raised to minus 2 plus big O of x log x. Okay, let's multiply this in to get x by 2 plus half of zeta of 2 times x square plus, here you can see this is big O of x raised to minus 2. You're multiplying that to x square by 2. So what you will get is big O of 1, big O of half, which is big O of 1 itself. Okay, so this is big O of 1 plus big O of x times log of x. But big O of 1 is the same as big O of x log x. Okay, so sorry, I'm saying 1 is big O of x log x. So this sum when you add up will be again big O of x log x. Okay, I have made a mistake here. Just to recorrect this, x log x. Okay, so this will be minus x by 2. Okay, another thing which you can also notice in fact is that minus x by 2 is big O of x, okay, which is big O of x log x. So all these three will combine this to give us big O of x log x. So we will get half of zeta of 2 x square plus big O of x log x. Okay, and this proves our result. Now for the corollary, we'll show that the average order of sigma 1 of n is big O of zeta of 2. Again, very easy. We'll take f of x to be 1 by x times summation n less than or equal to x sigma 1 of n. Okay, so if we take this you can notice that this is equal to half of zeta of 2 times x plus 1 by x times big O of x log x, which is half zeta of 2 x plus big O of log of x. Okay, and therefore f of x upon half times zeta 2 x, this would be what? This will be 1 plus 2 by x squared should be, okay, 2 by x square zeta of 2 big O of log x, and this will be 1 plus big O of log x by x square, big O of log x by x square. Now using L'Hopital's rule, you can see that this will go to 0, okay, as x tends to infinity. You can see that limit as x tends to infinity, log x by x square will be 0. Okay, x square is much faster than the log x, so therefore that will go to 0, and this tells us that limit as n tends to or x tends to infinity, f of x upon half zeta 2x will be 1. So they are of the same order, f of x and half of zeta 2x. So you can see that we now have even identified what is the order of sigma 1n. Okay, now let's look at sigma alpha when alpha is not equal to 1. So let us see what happens in this case. Okay, so in this case what you see is that summation n less than or equal to x sigma alpha of n, this will be summation n less than or equal to x summation d divides n d raised to alpha. This will be summation k less than or equal to x. We have proved this in the exercise. D less than or equal to x by k d raised to alpha. Okay, now this section here, let's see what this part is. This we have got in the result in the previous chapter, so notice that summation d less than or equal to x by k d raised to alpha, this will be x raised to alpha plus 1 upon alpha plus 1 times k raised to alpha plus 1 plus big O of x by k raised to alpha. Okay, so this is what you will get, and this tells us that summation d less than or equal to x by k d raised to alpha minus x raised to alpha plus 1, this is in fact by definition alpha plus 1 k raised to alpha plus 1, this will be big O of x by k raised to alpha. Now let us take the sum throughout by this sum throughout on both sides. What do we get? So therefore take that sum throughout, what you'll get is summation k less than or equal to x summation d less than or equal to x by k d raised to alpha minus summation k less than or equal to x raised to alpha plus 1 upon alpha plus 1 times k raised to alpha plus 1. This will be big O of summation k less than or equal to x by k raised to alpha. Okay, so therefore what you can see here is this part is the sum which we are interested in, that is summation n less than or equal to x sigma alpha of n. This would be equal to summation k less than or equal to x raised to alpha plus 1 upon alpha plus 1 times k raised to alpha plus 1 plus big O of summation k less than or equal to x by k raised to alpha. Okay, let us look at this sum here. Okay, so what we have, let us call this as 1. So summation k less than or equal to x raised to alpha plus 1 upon alpha plus 1 times k raised to alpha plus 1. This will be equal to, let's take out the constants. So you will get x raised to alpha plus 1 upon alpha plus 1 times summation k less than or equal to x 1 by k raised to alpha plus 1. This is what we have. Okay, now again using the result which we have proved in the last session, we will have, this sum here will be minus x raised to minus alpha upon alpha plus, please check that this is correct, this calculation. If you are not getting it, you can ask me. Okay, plus big O of x raised to minus alpha minus 1. Okay, so this will be, take this inside, you will get x raised to, your plus alpha minus alpha will cancel, you will get x, so minus x upon alpha square plus alpha plus you have zeta of alpha plus 1 divided by alpha plus 1 x raised to alpha plus 1 plus this will be big O of 1, because you can again multiply inside as we have argued earlier. Okay, so this here will be, here you can see this term is big O of x. Also anything that is big O of 1 will be big O of x. So this will be zeta of alpha plus 1 upon alpha plus 1 x raised to alpha plus 1 plus big O of x. Okay, so that's what you get here. Now what is the beta? Okay, we can see here beta is the maximum of 1 and alpha. So let's see what we get. Sorry. So now let's look at summation k less than or equal to x by k raised to alpha. Okay, that is, I am looking at, let me call this as 2. I'm looking at this part which is inside the big O. This part I will call 3. So this is x raised to alpha summation k less than or equal to x 1 by k raised to alpha. This would be x raised to alpha times x raised to 1 minus alpha upon 1 minus alpha plus zeta of alpha plus big O of x raised to minus alpha. This would be, multiply your x inside, you will get x upon 1 minus alpha plus, this is zeta of alpha times x raised to alpha plus, now here you multiply your x raised to alpha inside, you're going to get big O of 1. Okay, now let's see what this is. This here is big O of x. This is big O of 1, as we already know. This is big O of alpha, x raised to alpha. But beta is the maximum of alpha and 1. Okay, since this is big O of 1, this will also be big O of x. Okay, and since beta is the maximum of 1 and alpha, what you'll see here is every term will be big O of beta, x raised to beta. Okay, so this we can call as 3. And now you substitute 2 and 3 in 1, what you get is summation n less than or equal to x, sigma alpha of n will be zeta alpha plus 1 upon alpha plus 1 x raised to alpha plus 1 plus big O of x plus big O of x raised to beta. Okay, this here will be, again as I said, big O of x will be big O of x raised to beta. So this will give us zeta of alpha plus 1 upon alpha plus 1. Here we see, yeah, so x raised to alpha plus 1 plus big O of x raised to beta. This is what you have, and this proves your theorem. Okay, so let's look at the corollary to this. Again, the same approach. We are proving that the average order of sigma alpha of n is zeta alpha plus 1 upon alpha plus 1 n raised to alpha. So let's take f of x to be 1 by x summation n less than or equal to x sigma alpha of n. This is what we are taking. Therefore, what happens to f of x upon zeta alpha plus 1 upon alpha plus 1 x raised to alpha? This will be, okay, what is so let me write what this is. So this is 1 by x times what we had in the earlier part, that is zeta alpha plus 1 upon alpha plus 1 x raised to alpha. You can remove this, will be zeta alpha plus 1 upon alpha plus 1 x raised to alpha plus 1 by x times big O of beta. So 1 by x times big O of beta, sorry, x raised to beta. Okay, now what happens to f of x upon this term? So you're going to get 1 plus alpha plus 1 upon zeta of alpha plus 1 x raised to alpha plus 1, that is x raised to alpha times x, that is x raised to alpha plus 1, okay, into big O of x raised to beta. This is what you have. But this is 1 plus big O of, this full part here is a constant, okay, and you have big O of x raised to beta upon x raised to alpha plus 1, that is x raised to beta minus alpha minus 1. This is what we get. Okay, now we know that beta is the maximum of 1 and alpha, which means that beta will be less than 1 plus alpha. Okay, so beta we know is the maximum of 1 and alpha. So either beta will be 1 or it will be alpha. So in any case it will be less than 1 plus alpha. Alpha is a positive number, so it will be less than 1 plus alpha. So you know that, which means that this portion here will converge to 0 as x tends to infinity, and therefore you will see that limit as x tends to infinity of f of x upon zeta of alpha plus 1 upon alpha plus 1 x raised to alpha, this will be 1, because this part will converge to 0 and hence big O converges to 0. Okay, so this proves this result. So what have we done up to now? So we have seen the average order of Dn. That's the first thing that we have seen. That is the So you can see here, first we have seen the average order of Dn. We showed that that is log of n. We showed then that the average order of sigma 1 is half zeta 2 n. Then we showed that the average order of sigma alpha of n. Okay, here you can see sigma alpha of n, where alpha is greater than 1. So for 1 we have done, for 0 we have done, that is Dn. For 1 we have done. Now we have just proved for alpha greater than 1 is sigma alpha plus 1 upon alpha plus 1 n raised to alpha. And finally now we need to show we need to find the average order when alpha is less than 1. Okay, we have done for greater than 1, we have done for equal to 1, we have done for 0. Now we need to prove see what happens when it is less than 1. Okay, so let's see that when alpha is negative. We will look at when alpha is negative. Where is that? Greater than 1 is done. Oh, this is in fact going to work when alpha is greater than 0 and alpha is not equal to 1. Okay, this will work in this case. Let me just make the changes on my alpha is greater than 0 and alpha is not equal to 1. This works in this case. So the only thing that we have got now to look at is when alpha is less than 1. So that's what we will try to do. So what happens when alpha is less than 0? Or we are going to look at beta greater than 0, sigma minus beta, and let's see what this works out to be. So it can give us two values, that depending on beta. If beta is not 1, then it gives us this value, that is zeta beta plus 1 x, big O of x raised to delta, where delta is the maximum of 0 and 1 minus beta. And when beta is equal to 1, what you get is zeta 2x plus big O log x. So let's try to prove this. So the first thing that you need to observe is that summation n less than or equal to x sigma minus beta of n. Okay, this would be summation n less than or equal to x summation d divides n d raised to minus beta. This is by the definition of sigma alpha. Okay, this would be summation. Now we have d less than or equal to x summation k less than or equal to x by d 1 by d raised to beta. This would be summation d less than or equal to x 1 by d raised to beta summation k less than or equal to x by d 1. Okay, which is equal to summation d less than or equal to x d raised to beta times greatest integer x by d. So we have this. Now we know that we have proved this in fact earlier, that the greatest integer of x is x plus big O of 1. Okay, so using that fact, what we have here is this will be summation d less than or equal to x d raised to beta. Here what you have is x by d plus big O of 1, which will be this is a one by d raised to beta, right? This is 1 by d raised to beta. Okay, so this will be summation d less than or equal to x we can take x here, 1 by d raised to beta plus 1 plus big O of summation d less than or equal to x one by d raised to beta. Let's observe this sum here. Okay, so let me just look at this portion here. Okay, first let's look at the first sum, that is x times summation d less than or equal to x 1 by d raised to beta plus 1. Let's see what that gives us. So summation x times summation d less than or equal to x 1 by d raised to beta plus 1. What does this give me? This gives me x times x raised to minus beta upon minus beta plus zeta of beta plus 1 plus big O of x raised to minus 1 minus beta. This is what we have, and this will be minus x raised to minus beta plus 1 divided by beta plus zeta of beta plus 1 times x plus big O of, so when you multiply x inside, what you're going to get is x raised to minus beta. Okay, now notice here that this also will be big O of x raised to minus beta will be big O of x raised to minus beta plus 1. Okay, so using the transitivity again, what you have is this is zeta of beta plus 1 x plus big O of x raised to 1 minus beta. This is what you have. Okay, so let's call this as 2. Now in 1 we have this sum. Okay, but this sum, the formula, if you see, changes when beta is 1 and otherwise. So let me look at it in both cases separately. So let's add a page now. So what happens in the case when beta is 1? Okay, therefore what you get here is summation d less than or equal to x 1 by d. This will be log of x plus c plus big O of 1 by x. All of these terms are big O of log x, so this will be big O of log x. Okay, now therefore what happens here, you have summation n less than or equal to x sigma minus 1 of n What is this? This will be from 2, you take 2 and substitute in this portion. What you have now, your beta is 1, so this is going to be zeta 2x plus big O of minus 1. So zeta 2x plus big O of x raised to minus 1 plus big O of log of x. Fine. So this is what you have. So 1. Oh yes. So here you can see that when beta is 1, you have x raised to 0, that is 1. So this will not be minus 1, that was a mistake. So this will not be minus 1, this will be 1, x raised to 0, so that is 1. That is 1. Okay, now big O of 1, we know 1 is big O of log x, so this will be zeta 2x plus big O of log x. Let's see if we have got what we wanted. Let's go to the previous. So what happens here is when beta is 1, zeta of 2x plus big O of x, log x. That's exactly what we wanted. Let's look at the second case. So in the second case, what we have? Case 2, beta is not equal to 1. So in this case, summation d less than or equal to x, 1 by d raised to beta, this will be minus x raised to 1 minus beta upon 1 minus beta plus zeta of beta plus big O of x raised to minus beta. This would be big O of, again here you can see here, this is big O of x raised to 1 minus beta. Okay, so what we have here is this is a constant, so there is, it as well also be big O of, is that right? This will be big O of 1 minus beta. So this will be big O of 1 plus big O of x raised to 1 minus beta. Okay, but see what delta is. Delta is big O of is maximum of 0 and 1 minus beta. Okay, that is what delta is. Delta is big O of, sorry, is maximum of 0 and 1 minus beta. So in any case, both these are going to be big O of x raised to delta. Okay, so this will be big O of x raised to delta, both of them. So let's see what this gives us. So therefore what we have is summation, so this I am calling as 3b, right? This is 3b. If I call this as 3a. Okay, take 3b and take 2 and substitute it into 1. What do you get? So you get summation n less than or equal to x sigma minus beta of n. This would be zeta of beta plus 1 times x plus big O of 1 minus beta plus big O of x raised to delta. Okay, this is what you get. What is 2? It is exactly this plus that. Okay, now what is this? This is x raised to 1 minus beta, right? This would be x raised to 1 minus beta. Fine. This is x raised to 1 minus beta. Again, the same thing comes up here. this will also be big O of, that is x raised to 1 minus beta is big O of x raised to delta. So what you have here is zeta of beta plus 1 times x plus big O of x raised to delta, and that's what you wanted to prove, and this gives us a result. Okay, so this ends in fact yes, so with this we can end this chapter. You would want to see what is the average order of sigma, so I should write that corollary. So what is the average order of sigma minus beta of n? Okay, what is this? Okay, I will leave this out as a homework. You can very well observe it from this theorem. In two cases, take the two separate cases, check what is the average order. You can very easily see it. So I will leave this out as a homework for you. Okay, so thank you. We will end this session. Okay, and with this session, we end with this chapter also. Okay, so thank you.